Hello, I'm Rifath Khan.
And I'm Goncalo Regado.
We are PhD students at University of Cambridge, and welcome to Black Hole Wars episode number 5, The Rise of Information. Today we have Professor Suvat Raju from International Center for Theoretical Sciences here to talk about what's so special about gravity and how the information is actually stored in gravity and how it might be a resolution to the information paradox and the general lessons that we have learned from this paradox.
Suvat, thanks for coming and for joining us for this 5th episode.
Thank you. Thank you for having me.
So perhaps we can start exactly from there. We have discussed a lot about various ideas in gravity, like holographic principle, black hole complementarity, and how these things can solve or not solve the information paradox. Maybe one question that the audience has is, what's so special about gravity in the way it stores information compared to our everyday life experience?
Yeah, I think that, I think that's one of the key questions that we could try and address in this episode. The reason we are interested, after all, in the information paradox is, there is, of course, a question about, what happens to black holes, but really, astrophysical black holes don't really evaporate in a time scale that's, even comparable to the age of the universe. So really, the information paradox is an interesting question because of what it teaches us about gravity in general, and the puzzles it raises for trying to put together quantum mechanics and gravity. And at least I think that one of the most important lessons that the information paradox teaches us is the fact that in gravity, information is stored very differently from the way it is, or the way we think about information being stored in everyday life. In particular, one of the things that we have learned by studying the information paradox and many other issues around it is that in gravity, one should think of a principle of holography of information. And what that means roughly is the following. If you take like ordinary objects, so this computer in front of me, this computer in front of me has some information, and that information is in its hard disk. And there's no way one can access that information without opening or without reading the hard disk. And that's true of other objects as well. There might be some information in the room next door, but the only way I can find out what that is by going and opening the room next door and exploring it. And that's the way we usually tend to think about information. And that was one of the ideas that went behind Hawking's formulation of the information paradox, because Hawking's point was that there's some information that falls into a black hole. And once that information falls into a black hole, it's lost to observers outside forever. But one of the things that we learn is that this information is not really lost because gravity is very clever about the way it stores information. And in theories of gravity, there's a property which states that, you might have some information that's local to a region. So there might be some information that's inside the black hole. But gravity always retains a complete copy of the information on the outside. So that might sound like something very surprising. It's certainly very unusual from the way our everyday experiences work. But as best as we can tell, if you think about gravity carefully, and you don't even have to put in very strong assumptions, just from what we understand about the way quantum mechanics and gravity fit together, it is indeed true. And so, that is I think, something which is very exciting, which is very interesting. And it's a general lesson that holds even separately from black holes. And this is the idea that information in the bulk of some region is also available near the boundary. So, it would say that if I could, for instance, have some sequence of observers stationed on the walls of this room, then by making sufficiently delicate observations, they would have to make very careful and very precise observations, way beyond our current experimental ability. But if they could, then they could actually determine what was happening in the bulk of the room without directly exploring it. And that's something which is very interesting. And that, I think, is one of the main lessons we learn from thinking of the information paradox.
I see. So you mean to say, like, so I'm in this room, and so a copy of information about me and my desktop, everything would be stored on the walls of this room.
Right, right. So maybe I can show some pictures to try and I had some pictures, so maybe I can show some pictures for to try and make this a little bit clearer.
Okay. One question that I
Yeah,
have is,
go on. Yeah.
uh, if it's like the copy of this information is present on the walls of the room, does this go against this the no copying theorem in quantum mechanics?
Yeah, great. So let's talk about both of those things. So first, I just wanted to explain what what I meant by this copy of the information. So imagine that you have a setup of this kind. Maybe I go to presentation. Yeah, so imagine you have a setup of this kind. So there's some red ball that's inside, and you have some way of surrounding it with detectors. So you have a grid of detectors. So every grid point where the latitude and the longitudes and the sphere meet, let's say you have a detector there. And so let's say you have some way of surrounding some object with a grid of detectors, all of which are incredibly precise and can make very accurate measurements. Then the question is, you could try and ask, is the ball inside red, or is it green, or is it something else? Is it ellipsoidal, or is it spherical? And the claim is that that information is already available to these detectors that live on the boundary of this region. And so that's a sense in which gravity is very special. You see, even otherwise, even in ordinary life, you could wait for some time. You could wait for light from this ball to come out and emerge and hit these detectors, and then it would be possible to tell whether the ball was red or whether it was ellipsoidal. You could just wait for information to emerge. But the special thing about gravity is that at the same time, while the ball is sitting in the middle of the sphere, you can, by making observations on the boundary of the sphere, determine what's happening inside. So that's what's in some sense special about gravity. Here's a cartoon of how something like this might work for a black hole. So we have a black hole, and Hawking argued that information is lost. But at that time, this notion of how information is stored in gravity was not understood. And so the extension of what I said previously was that if you had this army of observers, like all these little stick figure observers who were surrounding this black hole, and all of them had detectors, then they would be able to determine what was happening inside the black hole without even waiting for the black hole to evaporate. And that is a very special property of how gravity stores information. And that's what's so remarkable.
So one question people might have at this point is, can one single observer obtain any information about the inside, or is it just a collection of all these observers together?
Right.
Once they communicate.
You need a collection of observers. If you just have one single observer, and then information could escape from the other side. So if you remove like the observers on one half of the black hole, then they would not have access to the information inside. So it's really a collection of observers who can surround the black hole, or who can surround an object which has information. That's true here as well. If I took away half of this sphere and I just had detectors on half of the sphere, they would not have information about everything that was happening inside. So you really need a collection of observers. Yeah, good. So the question you had was about the no cloning theorem. Exactly. So in quantum mechanics, there's a very important principle, and that's called the no cloning theorem. So just to explain what that is for the benefit of the audience, if the point is that in quantum mechanics, if you have quantum information in one spot, it is not possible to clone or to create an exact clone of that information in another system. And there's a reason for that, as we'll discuss a little bit later, maybe, and as many people maybe already know. In quantum mechanics, there is some notion of an uncertainty principle. If you tell me the position of some object precisely, then I don't know the momentum of that object precisely. But if you could create clones of a system, so if you had some system and you could just create clones, then you could start violating these rules, because you could say, I measure the position, and then I create a clone, and I measure I measure the momentum. And so it's very important that you should not have you should not be allowed to entirely copy quantum information. So you can have systems which are identically prepared, but for a given system you're not allowed to create clones. And that would also run afoul of another property in quantum mechanics, which is called linearity. So in this, in what we're talking here, there isn't a notion of cloning of quantum information. And that is because the degrees of freedom that live on the center are, in a sense, the same as the degrees of freedom that live on the surface of the sphere. And it's not that you have a clone, or it's not that you have, even though I use the word copy, it's not really that you have a separate copy which you can manipulate and you can make measurements on without disturbing the original system. But rather it is the fact that there is some relationship between degrees of freedom that live in the middle of the sphere and degrees of freedom that live outside. And this relationship is imposed by the dynamics and the constraints of gravity. And so if you were to make a measurement outside, you would automatically also make a measurement inside. So it's, I did use the word copy, and perhaps that's not entirely precise. It's perhaps the fact that, it's perhaps better stated in that there is another way to access the same information, which is by making measurements on the outside without making any measurements directly inside.
And how would this relation between the degrees of freedom inside and on the boundary actually come about? Is it does it have to do with the way the configuration inside is generated?
Okay,
or,
so that okay, so that's a great question, and I had some pictures on that as well. So let me try and so I'm going to try and take you through the argument in as non-technical a way, and hopefully it will be intelligible. And so I'm going to try and explain why it is that gravity is so special. So let me just start with something that I was saying here, about the uncertainty principle. As I said, in quantum mechanics, there's one of the first things we learned about quantum mechanics was that quantum mechanics has a notion of observables that don't commute with each other. And what the simplest setup in which one can understand this is in terms of just thinking of a particle. Usually in classical physics or in everyday life, when we think of a particle, there is a sense in which you have a particle, and the particle could be stationed in one spot, and at the same time you could also keep the particle at rest. So the particle could be exactly in one spot and it could be exactly at rest. But it turns out that in quantum mechanics that is not possible. If you try and squeeze the particle, you try and make measurements of the particle more and more accurate so that you know its location to great accuracy, then it turns out that you start losing information about its momentum. You get greater and greater uncertainty in its momentum. And because momentum is related to energy, the point is that if you look at something which is sharply peaked in energy, in that you look at some state in quantum mechanics which has extremely sharp energies, then such a state is totally delocalized. So that's the picture that you see in front, in that you have some state whose energy spectrum is very sharply peaked about one energy, and in position space, this state is just totally delocalized. It could be anywhere. So now, how do you get around that? Of course, there's a sense in which all of us are localized, right? We are not totally delocalized. And the way we get around this in quantum mechanics, and this also works in a generalization of quantum mechanics called quantum field theory, is as follows. We say, well, we allow some uncertainty in the energy. So we say, let's add up states. There's a sense in which you can superpose states or add up states which have different energies. So you take some state of some energy, you add up a state of a different energy, and then a third state of a different energy. And in fact, you can add up an infinite number of such states. I only showed 3 here. And if you added up some number of states, you could then get a localized excitation. So by doing this, you could get you could get some excitation, as you see on the right-hand side, where the probability for it to be found is very sharply peaked at one point and is almost zero outside that. So that's the way you usually localize objects in quantum mechanics. And that's why, we usually, we talk about information being localized. And what that really means is that, the information is comprised of some physical objects, and they have some uncertainty in their energy. And that, the states which constitute their energy states are added up in just the right way so that the information or the physical system just sits at one spot and it's localized. Now, yeah,
sorry,
go on.
What exactly do you mean by an excitation here?
Oh, did I say excitation? I was saying energy spectrum. I was saying that, I was saying that, let's say you had some information, or you had some qubit, or you have some physical system, and you want to localize it in one spot. So the way you localize it is, you think of states of that system which have different energies, and you add together those states. So, in quantum mechanics, all physical systems have a wave function associated with them. And you can think of wave functions that correspond to the object having different energies, and you add together those wave functions, and that gives you some wave function which has some uncertainty in energy, but which you can arrange so that it has a very precise location. And in terms of waves, what is done here is you arrange to have these different wave functions interfere destructively outside some region and interfere constructively only inside some region. And when you do that, you get a probability distribution of the kind you see on the right-hand side, which is sharply peaked at some point. So if you try and measure now this physical system, you will find it sharply peaked at some point.
So and now, this is the kind of behavior we'd expect for a generic system, not necessarily gravitational one.
Correct, exactly. So this is here. I was just explaining what happens without gravity, and now I want to explain how gravity is special. So now, how is gravity special? So in fact, gravity is special in a way that, in some sense, we understand. All of us are familiar with, and that is the fact that gravity has this property that you can measure the object, you can measure the energy or the mass of some object even from far away. And this sometimes goes under the name of what is called the Gauss law. It's the fact that, for those of us who are familiar with these terms, if you take the gravitational field of some object and you integrate it on some large sphere around the object, you can compute the mass of the object. But it's something actually pretty simple. It's the fact that, if you think of the fact that we know the mass of the sun, you could ask, how do we know the mass of the sun? We haven't sent any rockets to the sun. We live on this earth, and here's this big sun. And how do we know how heavy the sun is? And the way we know how heavy the sun is because we can measure the gravitational field of the sun. We know we know the attraction that the sun has on the earth and on other planets. And using that, you can infer the mass of the sun. And that's because gravitational fields have this property that, if you have some mass, you put some mass in one place, it attracts everything, and it continues to attract everything even far away. The attraction dies off, but if you go far away and you measure like the gravitational field, you can tell what's the total mass inside some region. So now this is something that's familiar to us also, but the funny thing that happens is that if you put together this aspect of gravity with the aspect of quantum mechanics that I described earlier, you come to this remarkable conclusion that it's very hard to localize information. So here I have a cartoon of how gravity behaves. If you take one of these wave functions I described previously, which has some energy, so you have some particle which has some delocalized wave function. Apart from the fact that the particle has some delocalized wave function, it has necessarily also has a gravitational field which extends all the way out to infinity. And so with the particle, you also have to think about its gravitational field. And now think of what happens if you try to do what we were saying you could do in quantum mechanics earlier, right? Where we said that you could add together wave functions of different energies so that they would interfere destructively outside some region and constructively inside some region. So let's say you try to do that, do the same picture that I showed you previously, where you had these wave functions which had different energies. So if you just think of the left part of this, and if you added them together, you would get something which was localized in some region. But now each of these energy states comes with a gravitational tail of its own, and the shape or the size of the gravitational tail is determined by what the energy is. So if the energy is higher, the tail is larger. If the energy is lower, the tail has a different value. And so you see that now each of these energy eigenstates also has some counterpart or has some perturbation or some gravitational field that extends all the way out to infinity. And if you did not have this field, you could have tried to make these states interfere destructively. But in the presence of this gravitational field, you cannot arrange to have that destructive interference everywhere. Because while you could arrange to have these energy states or these wave functions on the left-hand side interfere destructively, you would still be left with this tail far away, which would not interfere destructively. So that's a very it's not the most precise way of saying it, but it's the quickest way to try and reach this conclusion, which is that in gravity you cannot localize some object entirely to a region. You always have some tails which stretch out to infinity and which have information, in fact, not only about the total energy of the object, but in fact the details, the entire energy spectrum, and all the information about what the object is comprised of far away. So that is a surprising result, but it comes if you think carefully about the Gauss law, which is a special aspect of gravity, and the uncertainty principle, which is a special aspect of quantum mechanics. And so this feature of the loss of localization is an aspect of quantum gravity.
Uh, I'm Suvat. So let's take a theory with sorry. Let's take a theory with no gravity, and we also have this Gauss law for the electrostatic charges, right? And why can't we make the same argument and say that like we would also have an electric tail at the infinity, and so the localization would be different.
Excellent. So, the difference, of course, between electromagnetism and gravity is that electromagnetism, you have both positive and negative charges. So if you put a positive and a negative charge together, you can arrange for things which are exactly neutral, so that they don't have any tail at all that goes out to infinity. And because you have objects which are exactly neutral, you can, in fact, most objects, most operators, or most of the information content in a theory of electromagnetism resides in these objects, or in these excitations, as they say, which are exactly neutral. And because you have these states which are exactly neutral, those states don't have a tail that goes out far away. And that's the reason you can localize information in electromagnetism, but not in gravity. So it's the fact that in gravity, the charge, so to say, which is the mass, is always positive. There's no sense in which you can create something which is gravitationally neutral, because you can't. There's no such thing as a negative mass. If you did have negative mass, then things would be different. But to the best that we understand, in gravity, there's no such thing as negative mass. And so you can't create something that's gravitationally neutral, but you can create something that's electrically neutral. And that's the difference between electromagnetism and gravity.
I see. So what you're saying is that we can have different charge configurations in the center of the room with the same electric field configuration on the boundary.
Correct. And in addition to those charge configurations, you could add to it, for instance, photons, which would just not have an electric field at all. So in electromagnetism, apart from the charge configurations, you have like charge carriers. So you have the force carriers, and so you could add to it photons, and you would just not have the electric field counterpart of that at infinity as well. And there's no way you could tell from infinity what the content of the inside was. So there's some things you can measure from infinity, even electromagnetism. You can measure the total charge inside the room, but you can't measure the distribution of charge inside the room, because you can't tell, if there's some combination of positive and negative charge that's sitting up somewhere that's messing up your observations at infinity.
Okay.
So if you would like to summarize this, the reason if we were to localize a particle in gravity, and then at infinity, when we would look at the strength of the gravitational field, there will be some uncertainty in it. Is that correct? Because of the uncertainty. I see. And right. Because we measure particular strength of the gravitational field, that means we cannot have localized the particle.
Exactly. So, there'll be some uncertainty in the gravitational field, and by reading off that uncertainty, and in fact, by looking at correlations, like, you measure the uncertainty, and then you can also measure, something to do with the particle. And by looking at the joint probability distribution, which, as you say, has to exist because there has to be some uncertainty in the gravitational field, you can determine, like, what was the set of energy states that you added to localize the particle, and therefore you can determine, like, where the particle is. Exactly, that's right.
I have a follow-up question on that, and let's say there are two different configurations in the bulk. By bulk, I mean the center of the room, and those two different configurations are actually spherically symmetric. So they look the same when you look at it from any direction, or when you do rotations. But they are different, and the way in which they're different is in the radial direction. Like, for example, you can think of one configuration to be an object, a massive object, which is a ball, which is filled evenly inside, and the second configuration to be a ball which is just hollow on the inside.
Right.
Now, for both of these configurations, we know from the Birkhoff's theorem that the metric far away from it would be Schwarzschild, which means at least they would be the same. So does this not sound similar to the case where for the electric charges for different configuration you would have the same tail, and that screws up things?
Exactly. So that's a great question. So you see, you're right that in classical gravity, so that's why I said this effect was a quantum gravity effect. In classical gravity, all you can tell from outside is the total mass for exactly the reason that you mentioned. You have a Birkhoff theorem which tells you that you look at spherically symmetric configurations, which is the simplest case, and you can have different density distributions, but if you have the same mass, you go far away, you can only measure the total mass in the field. But remember that these different radial configurations precisely correspond in the quantum theory to what is the spectrum of what is the uncertainty in the energy of this object. You see, because this object doesn't have a given mass. Remember, right? It has some uncertainty in its mass because you can't exactly have something which is localized. And this thing you're talking about, which is the radial distribution of the energy, which is how much of the energy is spread out, or is it localized in a thin shell, is precisely what corresponds to the uncertainty in the energy eigenstates that make up this object. So there is associated with this density profile some spectrum of uncertainties in the energy, and it's the spectrum of uncertainty in the energy that you can measure far away. And there is no classical analog of this, right? Because in classical dynamics or classical gravity, you just talk about some density distribution. You don't talk about the uncertainty in energies. And it is precisely the fact that in quantum mechanics, there is a correlate of this density distribution, which is the uncertainty in energies. And that's what you can measure from far away. And that is not the same. So that's why Birkhoff's theorem does not apply in this situation. It does not extend in any natural way to quantum gravity.
I see. Just to clarify, so what you mean is that both of these systems would, for both of the systems, the energy spectrum at the infinity, the mean values for those energies would be the same, but you mean the width would be different.
Exactly.
For example, yeah. Okay.
Exactly. That's
I
right.
see.
Absolutely. That's exactly correct. And it's this
see.
width which doesn't have like a classical analog. This width is like a purely quantum mechanical effect.
Yeah. So that's interesting. So the same thing would also, I assume, would apply to black holes, is it?
Right, exactly. So indeed, the same thing applies to black holes. In fact, in some sense, this is precisely the issue with Hawking's argument for information loss. If you look at Hawking's argument for information loss, Hawking posited a notion of a principle of ignorance. He said, and Hawking was thinking along lines of classical gravity and quantum field theory. And he posited a notion of the principle of ignorance. He said if you had observers who are outside a black hole, they would not have any information about what went inside the black hole. And therefore, they should adopt, or they should have adopted, according to Hawking, a principle of ignorance for the interior of the black hole. And that's what led him to the notion of information loss. He said it would be natural for these observers to trace out, or what's called tracing out in quantum mechanics, where you're ignorant about one part of the system, the inside of the black hole. And therefore, all that they would see outside would be some kind of a mixed state where you had some uncertainty. And so even if you started off with a state which is what's called a pure state in quantum mechanics, where you have all information, by virtue of having to trace out the interior, you would lose information. And therefore, the fact that you have this copy, or you have this redundancy in description, which may be a better way of saying it, the fact that you have this redundancy in description in gravity, where there is a redundant copy of this information at infinity, tells you that that's precisely the point where you see that there's an error in Hawking's argument, and the fact that instead of a principle of ignorance, you have the opposite. You have some principle of information. So that, in some sense, is how this idea ties up back to the information paradox. It ties up back to the information paradox because it tells you have a principle of information and not a principle of ignorance.
Mm-hmm. So that's very interesting. So the idea that we cannot access information in the interior of the black hole, you're saying, is a purely classical one, and that if you include quantum effects, these observers at infinity would actually have information of what fell in and what happens inside. Is that correct?
Exactly. So the idea that you cannot access information in the interior is either a purely classical one, or it's a non-gravitational one. So it's true in both limits. It's true in the classical limit, and it's true if you include quantum mechanics and if you switch off gravity, or if you include gravity but switch off quantum mechanics. But it's not true in if you keep both quantum effects and you keep gravitational effects. And so then it's not true that you have a principle of ignorance with respect to the interior of a black hole.
And in Hawking's calculation, would I be correct in saying that he turned on quantum effects, but he switched off gravity? And that's why he...
Yeah, that would be one way of saying it, exactly. In Hawking's calculation, he was doing quantum field theory about a curve, about a fixed space-time background, which is how, and one way of saying it in the language in which we're discussing right now is that he did indeed think about quantum effects, but he switched off, or he thought about gravity in a classical perspective, and that he thought, there'll be energy which will be radiated, and that will cause the black hole to shrink. But he was thinking of gravity in a classical perspective, and that in a sense is what leads to the paradox. And so if one thinks about information in a full quantum gravitational perspective, then you see one doesn't have this principle of ignorance.
Mm-hmm. So does that mean that if you take all the quantum effects into account, including the gravitational ones as we've been discussing, there is no notion of information paradox as Hawking proposed it?
I think so. I mean, I think that, well, of course, that I think is what we would say. And we have various indicators that this is true, which come from different angles. And so, if you do take into account the fact that gravity localizes information very unusually, then there is no information paradox in the form that Hawking proposed it. There are, of course, many other puzzles and unsolved questions about black holes and the black hole interior, and there are still many interesting things that we need to understand. But in terms of the paradox as Hawking formulated it, I think we understand how we should address that, and also where the error in Hawking's argument was.
Okay, I have a follow-up question. In the first episode, Chandramouli spoke about the Knowhow theorem, and he mentioned that it was the classical Knowhow theorem. And when I asked him about is there a quantum analog of it, he said there isn't. So to me it seems like what you're saying is that as different configurations of a black hole with the same mass, or at least the mean value of the mass, charge, and the angular momentum, they can still have differences in the widths of the energy spectrum at infinity. Can I consider these as hairs for the black hole?
Yes, you could. So that's one way of saying it. Of course, in one of the last papers Hawking himself wrote was about a hair and a black hole. But the hair he was speaking about that Hawking and his collaborators Perry and Strominger were discussing there was a different kind of hair. They were talking about what's called soft hair, which is they were talking about an infinite number of conserved charges that exist about black holes, and they were talking about a certain kind of hair. But it's true that the effect I'm describing is also, you could refer to that as hair as well. That there isn't a Knowhow theorem, and in some sense there are tails, and there's this uncertainty in the gravitational field that exists outside. You do have to combine this, if you think carefully, in flat 4-dimensional spacetime with this soft hair that Hawking was discussing. But it's a slightly different kind of hair from the hair that Hawking was describing. So the answer to your question is yes, you could think of it in some sense as hair. But the term hair has been used in many contexts, and so one should just be careful about the usage.
So we've been discussing how the information in gravity is stored at infinity, but based on the slide you showed, it seemed like you need this whole army of detectors around it. So my question is, how hard would it be to actually obtain this information? And maybe it would be impractical in a way that makes the information inaccessible.
Yeah, so that's a great question. So you see, the thing is that in any case, so let me answer that in 2 steps. You see, as I was saying, for everyday life, as I mentioned several times, we should be able to ignore these effects in some sense. And the reason is that you might say that there's in some sense information inside the hard disk is accessible outside. But it requires like making extremely delicate quantum gravitational measurements to access this information, and that's totally impractical. And so it's much simpler to just directly try and access the information inside the hard disk. And so usually you can ignore these effects. Now, in the case of black holes, there's something very interesting that happens. As we've known for a long time, from the time of Bekenstein and Hawking, black holes have an entropy. This entropy is very large. For the sun, for a solar-sized black hole, this entropy would be 10 to the 77, which would be in fact much larger than the entropy of the sun itself. If you took a solar-sized black hole, it would have a much larger entropy. The point is that you do expect that the signals of this information to extract or to recover this information, you would need to make measurements which are exponentially accurate in this entropy. So that's, e to the minus 10 to the 77. So you'd have to make extremely accurate measurements in order to be able to extract this information. And so it is the case that, the information inside the black hole is available in a highly scrambled form. Uh, but that's just how it is. The difference between the black hole and between something like the hard disk is that for something like the hard disk, there's a limit in which we can switch off gravity, or we can switch off quantum mechanical effects, or we can switch off gravitational effects. And there's a clear sense in which it's much easier to access the information in the hard disk than it is, to get it using these quantum gravity effects. But in the case of black holes, that's not the case. Whatever you do to try and extract the information, whether you wait for the black hole to evaporate and collect its Hawking radiation, or you use these gravitational effects when the black hole still exists, you always need to make measurements at an accuracy which is e to the minus s. And this s itself is in some sense a quantum gravity effect. The fact that the black holes have an entropy is itself in some sense a quantum gravity effect. And so, this effect, or these effects are important if you start thinking about recovering information from black hole. It's certainly true that they're extremely small, and so in principle, you would never be able to really recover information. But that's also true, if you burn a piece of paper. In principle, you can collect everything, all the smoke that comes out of the paper, and recover what was written on it. But of course, you can't really. And so it's true that these effects are very delicate. It would not be practical, even if you manage to create much smaller black holes, to recover information this way. But the interesting thing is the fact that it resolves an in principle contradiction between quantum mechanics and gravity. It tells you there's no difficulty in putting together quantum mechanics and gravity. So of course, in practice, the formation and evaporation of a black hole would probably lead to information loss in practice. But in principle, we believe that the dynamics is reversible because of these effects. And so the in principle answer is important, because that's an answer which is important for other questions we ask about quantum gravity as well. And that was the significance of the paradox, was that it suggested there was an in principle obstruction to putting together quantum mechanics and gravity. And that's what we're now saying there isn't.
So this is an important consistency check, the fact that you can, in principle, at least extract this information.
Right. It's an important consistency check. And as I said, it's an interesting lesson for quantum gravity, even otherwise. Let's say at some point in the future, we all hope it happens in our lifetimes, but at some point in the future, we actually are able to test quantum gravity, or we're able to find some system which simulates quantum gravity, and we try and test it. Even then, testing the unitarity of black hole evaporation might be something very hard. But testing this principle of holography of information, checking the fact that you have information somewhere, and can you in principle detect it by making observations around the object and not probing the object directly? That might be easier to check than checking unitarity of evaporation of black holes directly. So this is an interesting lesson which in principle we could have learned without thinking about black holes, but we thought about it because we were thinking about black holes. And so I think it's an interesting in general lesson for quantum gravity, and even for for tests of quantum gravity whenever we come to them.
So from what you said right now, it seems that the complexity of how hard it is to extract the information scales in some way with how much information we're trying to obtain. So would I be correct in saying that it would be, even though it's hard, it would be easier to extract the information of a hard disk than of a black hole from these effects?
Well, yeah, so it's certainly true that the complexity of the information, of how hard it is to extract the information, scales with how much information there is. So that's certainly the case. But there's another effect which I perhaps wasn't very clear about. It is the fact that you also have to compare now the complexity of trying to extract the information directly versus the complexity of trying to extract the information using these effects. So for a hard disk, maybe the hard disk is encrypted, in which case it's hard to extract the information, but that complexity is still much lower than trying to extract the information using these effects. But in the case of a black hole, even if you waited for the black hole to evaporate and tried to collect the Hawking radiation, there's a complexity which would still involve, quantum gravity effects, because the entropy of the black hole itself, has a factor of what's called the Planck length. So it's the area of the black hole in Planck units. And therefore, for a black hole, these complexities of trying to extract the information directly by waiting for the black hole to evaporate, or just trying to collect the information when the black hole still exists, these complexities start to compete, which they don't for other objects, because there's no other object which has, a 1 over, or some area over Planck length squared as its entropy. Some other objects just have some entropy, and Planck scale is separate. You can set the Planck scale to 0 and keep the entropy of the object finite, which you can't do for gravity. So that's all I was trying to say.
Makes sense. Yes.
That's interesting. Uh, if at all we would be realizing this in the real world, we would want the detectors on the boundary. We would want the boundary to at least be like finitely far away, or finitely compact in size, not at infinity. This whole construction work even if the boundary is not at infinity and at a finite distance.
So you would hope so. So, in the mathematical arguments we have for it, it's most convenient to define something at infinity. But you would hope that, and to the, you would hope that if you looked at the walls of this room and you had some excitation which was much smaller than the room, then effectively you should be able to think of the walls of this room as being at infinity. I mean, this is something that happens in classical gravity as well. You often do analyses of gravitational waves at infinity, but really, we're not exactly at infinity. There's some gravitational wave, it's still coming from a finite distance away. And so in gravity, it's often convenient to do these analyses at infinity, but you hope that the same analysis should work provided you're looking at an excitation that's small enough and you're at a distance which is large enough compared to the excitation. And to the best that we understand, there should not be a subtlety there, but there could be, because as we've discussed, there are many times when we've thought about quantum gravity and thought there shouldn't be a subtlety, and there was a subtlety. So certainly the hope, if you wanted to check this, would be that something like this should work to a good approximation, or to as accurately an approximation as you like. Even if you're in some finite size region, you should be able to treat the walls as if they're at infinity, even though they're not exactly at infinity.
So this would be an analogy with the solar system not needing to go to infinitely far away from the sun to determine its mass. We can just be at the distance we are from the sun right now. To a good approximation, we can determine it.
Exactly. I mean, if in classical general relativity, for instance, if you open some of the textbooks, they'll tell you that there's no way to define a notion of local energy. You always have to go to infinity to define energy, even in general relativity. But of course, that's not really true. We talk about the mass of the sun or some notion of local energy without being really at infinity. So provided you're far away and the gravitational fields are weak enough, you hope that something, you should be able to think of that as infinity.
One question that people might be wondering about is, they have heard in the previous talks that nothing can travel faster than light. And now here we seem to be saying that at the given instant of time, we can just, by looking at the measurements on these detectors, determine everything inside without waiting for information to reach the boundary. Doesn't this contradict this maximum speed in the universe, the speed of light?
Yeah, that's a great question. So I had some pictures. So let me try and share those pictures. So here is the configuration I was talking about, right? So I said that here you had some ball in the middle, and maybe it was red or green or orange, and you had these detectors that surrounded it, and you had to tell me the shape of the ball and the color of the ball and so on. And I said, by making these observations, you could tell that color at the same time slice or the same time instant. But of course, if you think about it, as we've discussed already a few times, you need an army of detectors, an army of observers. So you need to make observations on every point of this surrounding sphere. And now, you also have to then combine these observations, because one of these observations by itself doesn't give you information about what's happening to this ball in the middle. You need to combine these observations. And if you ask how much time it takes to combine these observations, it means that an observer on the North Pole has to signal to an observer on the South Pole of this sphere in which you'd station these detectors. And that, in fact, takes as much as the light crossing time of the sphere itself. And so, in fact, for all of these observers to be able to combine their observations, takes much longer than it is for them to be able to do their observations. So the remarkable thing here is that they don't actually need to have their detectors on for more than a short time instant. But afterwards, they do need to process their observations, and that, in fact, takes as much time as the light crossing time of the sphere. And so that's one answer. So it's not really the case that these observers can get information instantaneously, because they just make some detection and they don't actually have any information till they combine this detection with the detection made elsewhere, and that takes as much time as it would for the light from the ball in the middle to emerge. So the interesting thing is they don't need to keep their eyes closed their eyes open at a later time, or the detectors on at a later time. The detectors are only on for a short time instant, and then they need to process. But it still takes the same time as if you had your detectors on at a later time. So that's one answer. But in fact, there is a deeper answer. When people or physicists talk about these issues of causality, you always want to have a precise notion of causality. So these kinds of hand-waving arguments I gave you right now are not always very satisfactory. So let me try and say something a little bit more precise, which tells you that you really need to think about these issues of causality a little bit more carefully in gravity than in quantum field theories. So, in how do you test causality, or how do you test superluminality in a theory without gravity? So the way you test it is as follows. You think of some state. You take a system and you prepare some state, and you prepare a state so that the state of the system is identical outside some region. So it's identical outside this white circle. So let's say you look at the picture on top. So in one, you have like one shaped bump. In the other, you have a different kind of bump. And outside the bump, the systems are identically prepared. So they're just entirely identical. So that's what the picture on top is meant to show you. And then you can wait for some time till you reach the picture below, where both the bumps have spread out a little bit. And both the bumps have spread out. So the bump on the left has spread out and the bump on the right has spread out. And you could ask, what is the rate at which the region in which they differ is growing? And that region should not grow faster than the speed of light. And that is really, how we check superluminality. So, in fact, every experiment you do to test superluminality, you can phrase in this language. You can say, you show a red flag or you show a blue flag, you have a detector outside. The detector outside has to see which flag you showed. That's a situation of this kind, where in one case, instead of a bump of different kinds, you have flags of different colors. The state outside is identical in that the detector has no information about the state. And then you wait for some time till that information reaches the detector, and it should not reach the detector faster than the speed of light. So really, this is the way we define notions of, or this is the precise way in which you can ask questions about superluminality without gravity. But in gravity, you have to be careful because you can't even set up the configuration on top. So if you try to set up these bumps of different shapes, as I said, each of them would have some tail associated with them. So this bump of one kind would have a tail of one kind, which would extend all the way out to infinity. This bump of the other kind would have a tail of a second kind, which would extend all the way out to infinity. And these tails would be distinct. So you cannot set up a situation where, you have some difference inside some bounded region and everything just identical outside that bounded region. And so, you have to be much more careful about what are the precise questions you can ask when you ask questions about superluminality. So one example of a question that you can ask is, you can ask, if you go to infinity, can you then, you could prepare, for instance, some states which were different on the left of some region and were entirely the same on the right side. And that would be, that would be okay. That wouldn't contradict this principle I discussed, because the left extends to infinity and the right extends to infinity. So you can try and think of states where two parts of this boundary are prepared differently, and then you could ask, how fast do these regions of difference grow? And so there is a sense in which, even in the theory of gravity, what we call asymptotic causality is exact. So if you go asymptotically, or you go asymptotically far away, all these effects kind of become unimportant. There's a sense in which you can prepare one part of the boundary completely different from another part of the asymptotic boundary. But you can't do it for these geometries that we see here, or the geometries that we had above, where you prepare something differently inside a bounded region and make it identical outside. There's a technical way to say this. The technical way to say this is that in gravity, we don't have split states with this configuration. The fact that without gravity, in quantum mechanics, you can prepare configurations of this kind, which differ inside a bounded region and are identical outside, is what's sometimes called the split property of quantum field theory. And in gravity, we see that we can't have these kinds of split states. So there are answers at two levels. The first answer I gave you is that you have to be careful, not just in terms of when you make the detections, but in terms of how long it takes to process information. And that's a hand-waving argument to tell you that you can't really communicate faster than the speed of light. But there's a second fact, which is the fact that you need to think more carefully about causality. And in the bulk, you have a hard time even defining causality. But there's a sense in which you can define notions of asymptotic causality, and those are exact to the best that we understand, even in gravity.
So if we go back to the picture of gravity, with gravity, so the other slide,
right.
Is it the case? Would I be correct in saying that if I try to build up a configuration, for example, of a black hole in the middle, just sitting there, and another configuration of, for example, two black holes merging, which is very violent, very different. Intuitively, I would think that, oh, I have to wait until the information of the merging to reach the infinity for me to be able to tell the difference. But what you're saying is, well, at all times, whenever I look, it's already there. I can already tell.
Exactly. That's exactly right. And there is, you can so the information is always outside. I mean, that's what this slide is supposed to say, that if you prepare a state in some way in the interior, there is a sense in which the information about that is just always living outside. As there's a more dramatic way to say this. Sometimes people say, what if you're on the surface of the room, you have these observers, and I'm in the middle, and I decide at some point, to switch on a light or not switch on a light, and that's a decision I made, and how will you know whether what decision I'm going to make? But of course, if you take this theory seriously, then the answer is that the information of what decision you're going to make is also always there on the boundary. So it's the information about the entire state, including the state of this person inside who thinks that the person is making a decision, is always there on the boundary. So it's certainly true for black holes, as you said. And what I said right now is a more dramatic way of saying this. The fact all information in the bulk is always there in the boundary. So it's not that the information about what decision you were going to make propagates faster than the speed of light to the boundary. It is the fact that that information was always just there at the boundary. And so that's,
the observer is like a big brother. They already know what you're going to think and do. Just by being
that's right. Exactly. Right. So you already know what you're going to think and do. So of course, I mean, just to emphasize, these are not like practical considerations. But in principle, that's what the theory is telling you, that there is a sense in which that information is already available outside.
So does that mean that you don't have free will in the bulk?
Well, yeah, those are yeah. So now we're probably going to like I mean, yeah, maybe we should not. It'll lead us.
Yeah, I was going to ask this question, but then I thought maybe not. It'll be depressing.
Maybe we should. I think we'll go astray, and then we'll start discussing like
Let's edit that question out. Okay.
Yeah, maybe we should edit.
Yeah.
I mean, everyone likes this question, right? Does physics allow free will or not? But then, we'll just end up discussing that. So that's not.
Okay, Suvat, can you go back to the split?
This one. Yeah.
Yes. So what you mean to say is that in the first two figures on the top, there is this boundary between which you have this yellow flat surface, and inside that boundary you have these packets being different. And you mean to say that boundary, that region in which these two configurations are different, that region cannot expand faster than the speed of light, as in obeying the causality.
Exactly.
That's what you mean to say.
Exactly.
Okay. So my question is, you also mentioned that in gravity, you cannot have these split states, but what you can have is two different configurations which agree on a part of the boundary.
Right.
Can that part of the boundary expand or contract faster than the speed of light with respect to the boundary? Like, does it obey the boundary causality?
Exactly. I think, yeah, it does. So to the best we understand, that is the most precise sense in which you expect that causality will hold in a theory of gravity. It is the fact that if you go to the boundary or you go asymptotically, then a notion of what's called microcausality, the fact that operators at space-like separation commute, becomes exact. So you can create such split states on the boundary, in that you could think of configurations which differ on some part of the boundary but are identical on another part of the boundary, and then you could ask, how fast on the boundary do those configurations, does this region of difference grow? And then it should be just the same as it is, in a theory without gravity. So if you go to the asymptotic boundary, then these effects that I'm mentioning should not be important. So this effect, the fact that you don't have split states, is something that's important in the bulk. But it's true that if you go far away to the asymptotic boundary, then causality is exact. or you believe microcausality is exact. So you really have the same notion of split states that you had without gravity.
Okay, so it looks like the Hawking's original formulation of the paradox is well understood, and we now understand how in the quantum theory of gravity, information is stored differently, and why the paradox doesn't hold anymore, and it might be a resolution to it. But is there any thing more that remains unsolved in this information paradox scheme?
Yeah, certainly. In fact, I think when people talk about the information paradox, they're not actually referring to one paradox. They're referring to a web of interconnected puzzles about black holes and the interior. So I think it's true that, in the formulation that Hawking originally had, I think we understand quite well what the error in that argument was and how we should resolve that paradox. Yeah, so we have these very well understood, or what we think are very well understood examples of holography. One of them is this something that's called the ADS-CFT conjecture. And even in these very well understood examples, we don't understand some questions about how one should describe the interior of black holes. We understand in some sense, if you look from outside, in what sense the information should always come back. But there are some questions about the interior of the black hole that we don't understand. And some of them might be very interesting questions. They might tell us that maybe to ask questions about the interior, you need to be careful about the fact that if you have an observer who goes into the interior, this observer is part of the system. There might be a sense in which you might have to you're asking a very different question from the kinds of questions we usually ask in quantum mechanics, where you have an observer outside who has a system, and the observer can separate observations from the system itself. But if you start asking questions about the interior of a black hole, or what happens to an infalling observer, then these questions involve a different kind of framework. Here you're trying to ask in quantum mechanics, what happens to a system if you look at it from inside? And these questions might also be relevant for a cosmological setting. We in some sense, we live in the universe, and if you want to talk about the way function of the universe, or why things around you look the way they do, we are asking questions which are slightly different from the usual framework of quantum mechanics. And it might be that black holes again give us a handle to ask these kinds of questions, which usually we don't really have a good handle to try and ask. But maybe black holes again tell us how we should think about such questions. So I think there are many unsolved puzzles about black holes which remain, and black holes, I think continue to give us a place where we can develop and understand our ideas. And in the end, I think we get some general lessons, like this lesson about localization of information in gravity, which we can then apply to settings without black holes. And so that's why it's interesting to think about these puzzles and paradoxes about black holes. And there are many such which remain, including this question about the interior, as I just mentioned.
Great, thanks for your thoughtful answer in the end. I think this is perhaps a good note to end this series of talks. So for those of you who attended these 5 episodes, we started from this very controversial paradox proposed by Stephen Hawking. We learned in the meantime about many crucial concepts in theoretical physics, like information, entropy, the holographic principle, and so on. We tried to explore some of the solutions to this paradox, and we even realized that maybe the paradox was not as problematic as it seemed at the beginning, and that we've learned so many lessons about the way nature works just by thinking about it. So if you take away a lesson from this, is probably that quantum gravity is cool and you should join research in the future.
And also, if you want to learn more about the information paradox and the lessons that it has taught us, there's an awesome course, and the link is down below. It's by Suvat Raju, and he talks about all of these things in great detail with all the technicalities. And we also thank all the organizers, especially Angaran, and all the speakers for the talk, and the students who participated in the questions. Thank you, and see you again. Have a good night.
Thank you. Thank you.